Good afternoon, everyone. I welcome all of you to the third Exun Talk session. Founded in 1992, Exun is the Computer Science and Technology Club of Delhi Public School, Arkipuram. The word Exun is short for Experts Unlimited. We hope these sessions are enlightening. We have a variety of speakers, and you can check out the full lineup on our website. Our speaker for today is Shashwat Goel, former president of Exun and a sophomore at IIT Hyderabad. He will be delivering a talk titled The Ubiquity of Graph Theory. And so, without any further delay, I'd like to invite Shashwat.
Yeah, hi everyone. So this is Shashwat Goel, and Vinayak has already introduced me. So I'll just only say a few words about myself. So I was a member of Exun for about 5 or 6 years, and yeah, and I've basically been part of the tech circle for a long time. And today I'll basically be talking about graph theory, um, and just at the outset, I want to make one thing clear. So, graph theory here, I'm not talking about the graphs you've probably studied in school, which was more about like bar graphs, statistics, and those kind of things. By graphs here, I mean networks. And basically, these sort of talk about connections between different things, and I'll get into the exact definitions and details later. So just a little bit about the talk before I begin. So I'll start by telling you how I got interested. So back in like grade 8 or something, I presentation for this math exhibition, and back then I knew nothing about graph theory. It's kind of like just like I'm pretty sure a lot of you go to competitions and you give presentations. So I basically read about it and gave a presentation. So that's where I started, and then so I was involved in competitive programming for a couple of years, and I graph theory basically became my favorite topic there. That's where I solved a lot of problems related to graph. Studied a lot about the different properties and topics that come under graph theory. And finally, like now I'm studying computer science. So I'll like it's a very fundamental part of computer science. A lot of applications basically are based on graph theory, and I'll be taking you through some of them in this talk as well. And about the talk itself, it's going to be very introductory. I'm not going to dig too deep into the actual theory, how actual like math, how the math works, how the algorithms work. Instead, my aim here is to like try to motivate you guys into like to basically make sure that after this talk, a lot of you feel like actually going and exploring these things on your own, because there's a lot of content available online, and you guys basically know that everything is like just a search away. So you guys can always look into that, and towards the end I'll also mention things that you can explore. And yeah, I'll mostly be focusing on the main ideas and like the applications. And so the format is going to be that I'm going to first like do a sort of a monologue. I'll give the talk, and then you guys can keep putting your questions as they come on in the comments, and towards the end I'll take all of them towards the end. Yeah. So so one thing that was part of the talk description, and I basically claim that I feel that every high schooler should know something about them. And it's kind of a bold claim, because like, and so so basically what you need to know in high school is something that can be applied in a lot of places, because you don't know what you're going to grow up to be, right? And your like things that you learn about in high school are kind of like the least common denominator of of everything that's out there. So should be one of them, and it's actually a field of mathematics and discrete maths, and like I think discrete maths is not exactly covered, at least in the CBSE curriculum. So those of you who are in CBSE won't have actually heard a lot about it, but it's actually quite applicable, and like it's used in, at least in CS, it's used in discrete math heavily. And it's kind of sad that it's not touched in high school, but it's also kind of good in some ways, because like maybe if it's not taught well, you'll not find interest in it. So maybe it's better that you can learn it on your own. Basically, like, even though it's a math subfield and it's applied a lot in CS and also other fields, but mostly in CS from what I've seen, it's surprising that you've probably only seen a form of them in physics and chemistry. So in physics, you've seen circuits probably, and a lot of and circuits are basically graphs, right? So basically your wires. So I'll come to the terminology later actually, but circuits are basically graphs. There are connections, there are nodes, which basically could be any of your devices, your bulbs or your resistors and all. And in chemistry, you've seen molecules and all. So like, obviously not all of you probably have studied science, I don't know, but these are two places that I know they come up. They might be coming up in other places. That's why I have this asterisk on my presentation. So they probably come up in other places, but you've mostly seen them in physics and chemistry, I guess. And I'm pretty sure you've solved maps. You've looked at maps, so they are forms of graphs. I'll come to how that is later. And you've probably also solved mazes. So yeah, that's basically all under graph theory. So I'll start with the definition actually. And so basically, all that you need to know about graphs before like actually understanding anything is that there are these things called nodes, which basically are your which basically contain information about your about the state of the graph. Like basically, if let's say if you're looking at a map, then cities would be nodes, and you could think of edges, these things called edges, as roads between cities. And I'll actually give you an example of that. So suppose, like, let's take the scenario of the postal service, right? Like so I'm not sure how many of you sent mail physically, but I'm pretty sure you know about it. So you could say that each of these nodes are actually mailboxes, or I'm not even sure if you have mailboxes these days, but whatever. These could be your physical mailboxes, and these edges could be basically roads, and a mailman comes, takes some letters from here and takes it to the other node, and things like that. And so obviously, like, one scenario is that there's only one van, there's only one source where the writer of the letter, and you have to send it to some destination, and the van just goes from here to here, then basically takes it to the destination. But it's actually obviously not as simple as that, right? Each road is of a particular length. So these edges basically may have a certain weight or a certain cost. You could think of it as a distance. You could think of it as the amount of petrol you have to spend, something like that. So these edges will always have some information on them, and the nodes can also have information on them. For example, like if it's one mailbox, you might want to track how many letters it has. And if it has more letters, maybe you want to prioritize this mailbox. And things get complicated very fast. Like, obviously, if you have just one van and one letter to take from one place to the other, that's easy. You can just find one path and do it. But what if you have hundreds of vans and you have hundreds of these nodes, and there's like different demands? Basically, one, you want to take A from this point to this point, letter B from this point to this point, and so it gets pretty complicated pretty fast, and things to see that things can get very interesting soon. So, and even this simple model of nodes, edges, and weights can get pretty hard. Like, it's actually not trivial sometimes to like figure out what the nodes will be, what the edges will be, and what the weights will be. And actually, if you can just figure that out, a lot of your problems can get solved, because there's a vast, like, you have a variety of theory available, like, that you can just search up. So if you want to find the shortest path from one place to the other, you can do that with an algorithm. All these things exist. The thing that won't exist when you like set out to apply graph theory would be things like no one will tell you what your nodes are, what your edges are, and what your weights are. And I'll just describe through some examples how that is hard. So take the problem of object detection. Like, if I give you an image and you want to basically figure out like you want to identify the cars, you want to identify the bikers, you want to identify traffic lights, you want to identify trees, all these things. Like obviously, so you can probably see why these are important, right? This is an important problem because you can think of a lot of places where this can be applied. Take self-driving cars, they probably need to identify these objects to avoid them, right? And that's where these things, this is an important problem. And you can actually like try a very naive approach using just what you've learned till now. Like you might think you've not learned anything, but you can actually break this whole thing into a graph, and that might not be obvious to you, but I'll just show that to you through this example. So what if I like break this image into a grid, like put this image on a grid, and now I could say that each cell in this grid is basically a node, and two adjacent cells are basically have an edge between them. And now and obviously this is like a huge grid, and you probably won't figure out a lot through this graph, but you could say that each pixel is a node. And once you have that, then you can do a lot of things, because for each pixel you probably also know what the color of the pixel is in, let's say, RGB values or a hex code or something like that. So yeah, so and now if you like put an edge between pixels that have the same color, and you start basically using that, you can basically like traverse your whole graph. You can go from one node to the other, and basically figure out these objects. So here your heuristic is that things with the same color are basically one object. And obviously you can see that this
Hi, I'd like to apologize. We're currently facing some technical difficulties. We'll be back as soon as possible.
yeah, so sorry guys, I think my net dropped or something went wrong. So I just continue with so I think I got through with the slide. So yeah, I was talking about how you can detect objects through graph theory, and like hopefully you got that part. So next I was talking about how you can like how Google Maps uses graph. Basically, it's like quite easy to think about how Google Maps would be using graphs beneath it, right? So like here I have I have two nodes. Basically, I've taken DPS Jammu at the very north of India and DPS Kolam at the very south of India. And I basically, like, Google Maps gives me a path between them within minutes, basically. And it claims that it's actually a very fast path and basically the least time that you can take from one place to the other. And yeah, so basically, it's actually interesting to think about how Google Maps does it, because I'm pretty sure you know that Google Maps can basically resolve things to the level of each individual address. It can like look at your it can basically spot the exact location of your house, and like just imagine how many houses there are in India. So there are 1.2 billion people. There are probably, like, let's say there are 500 million houses, and even if houses, like, probably houses take only 5% of India's actual land area, so that's basically like a lot of nodes. If you start making every house in this graph a node, even that is a lot. And since you also have to include roads and stuff, it can easily blow up very easily. And once it blows up into a lot of nodes, actually, so the hard part of selecting nodes and edges and things like that are that you want to keep the number low. You don't want a graph that is so huge that it takes your computer or whatever is computing it hours to give you a result. Google Maps has to do it in seconds, or otherwise we'll just close the app and move on, right? So it's interesting to think about how they split that whole thing into nodes and edges. And so the basic idea is that you don't actually need to take the house level for something like this, right? When you have to go from Jammu to Kolam, you don't really need to look at each house. And think of it logically, like if you want to go from Delhi to from your home anywhere, and you want to go to, let's say, a state that is a particular home that is in a particular state which is different from yours. So will you like start thinking about the exact path to that from one home to the other? You probably won't. You will first try to figure out so for example, if you want to go from Delhi to Chandigarh, you'll first like figure out that, okay, I need to take a particular path towards Chandigarh. And once you reach Chandigarh, that's when you'll start thinking about, okay, where exactly do I want to go? And that's actually very similar to how Google Maps does this. It basically has it first like takes bigger areas as one node. So you'll have, like, let's say one node is representing 1 kilometer square of area. And then as you like zoom in, it'll start breaking that one node into a lot of different nodes. And that's basically how it handles this whole complication. And even the edges here are not very clear, right? Like which roads are roads, which roads are just something that you can't take a car in. So those things also matter. Like picking edges can become complicated. Also, like edges, as I said, can have weights. And here you have to think about, what is your weight? Is it distance? Is it the time taken? And if it's the time taken, you have to obviously account for the traffic, which keeps changing every minute. So transforming a normal scenario into a actual graph that you can start computing on is non-trivial. It's actually the hard part, I would say, because after that you just need to plug some algorithms that are available online, and there you go, you can start from there. But yeah, and the last example actually I'll take here is of mazes, because I'm pretty sure you've seen them. And so this is a maze on the bottom left here, and you can see that you have to go from here to all the way to here. And so, like, as humans, we can obviously solve these small mazes, but you've probably seen that how larger mazes get complicated. And if you like increase the size even more, if I make a maze basically even as big as my computer screen, that will get pretty tricky. So you want to use algorithms to solve them, for example, maybe. So again, you have to, if you want to solve it using graph theory, you have to define the nodes. And looking at a plain maze, it might not be simple to see what the nodes are and what the edges are before you can actually start computing a path. So like one idea that is actually shown here is that you can split the whole maze into these, something like a grid, like we saw a grid in the object detection thing. So a similar grid like that. So each of these blue cells is a node, and adjacent cells have an edge between them, and you can basically traverse this grid. But again, like you want to minimize the number of nodes and edges you have in your graph. Like I talked about earlier, you want to make your algorithms faster. So so another way of looking at it could be something like this. Maybe you could, so here you have these very thin cells, and these are probably redundant, right? You don't want rows of cells which basically don't matter to you. So you can club all these small cells together and make a bigger grid. And this is actually quite better. This actually like works to some extent. And but you can do even better than that. So basically, what if you basically connect, you put a node near every wall. So here you have this wall in the maze and you put a node adjacent to them. So instead of making like 10 nodes here within this block, which using these cells, you can instead just keep it, just use 2 nodes and connect them with an edge. And now you actually need weights on the edges because the edges might not be of the same length. Because like technically I could connect this whole node to this node without having these 2 nodes in between. So that becomes a long edge basically. So there's this, so here you have a concept of weights. And if you want to like figure out the shortest path from the start to the finish, now you have something that's a little different. You have weights on these edges, and there are obviously algorithms to compute these. It's like one of the famous ones is Dijkstra's algorithm. And I won't go into the details of how those work here, but you can always check them out later. They're pretty simple to understand. So this is just an example of how a maze can actually get solved. So here it starts, and you basically start exploring using something called breadth first search. So basically you have multiple points where you currently you can reach in, let's say, distance 5, and then you want to see where you can reach in distance 6. So now it's like split into 3 forks basically, and it's exploring all of them simultaneously. So you can basically see how it will end up exploring the whole grid and eventually reach this destination. And interestingly, like this simple mechanism, like first start from a node, go to nodes that you can reach in distance 1, then go to the nodes that you can reach in distance 2 from those the earlier nodes. And just this simple algorithm can actually give you the shortest path from one node to the other. And like I won't go into how that's proven, but I hope it's like sort of intuitive to you that if you just increase step by step, you can find the shortest path from any source to any destination basically. And it like in 4 words, I would just say the algorithms keep expanding your horizon. So yeah. And obviously there are other search techniques you can use here. So if this was your starting point, you could like go from here, like just explore, just keep going deep into one path. You hit a dead end here, then you go back, then you try this path, hit a dead end here, go to this path and come back again because you've not reached your destination. And then you could like finally go towards the actual destination. And this is something called depth first search. So again, I won't dig into details, but yeah, that's another strategy, but that doesn't guarantee you the shortest path. So now I'll just jump to the applications here because like I want to, like I said earlier, I want to defend my claim that all of you need to know about this, right? So I'm going to like show you applications ranging from like social science, which you can see here, to basically pure sciences like I've already talked about physics, chemistry. I'm also going to show you something related to biology, and also I'll obviously take you through the applications in computer science. So if you see the graph here, it's basically showing the spread of misinformation. This is for a particular event related to election fraud back in 2016. So you can see some nodes here which like are very central to it and which start spreading these things from one user to the other user. So all these nodes are users, and probably the bigger nodes here show that these users were actually influential in spreading the fake news. So, and I'm pretty sure you know why this is an important problem, right? It's really important to society because these things can change how our governments work, how society functions. And so yeah, so you can basically compute how it flowed from one place to the other. And there are 2 key concepts here. One is of degree. So for example, let's say we're taking CNN. CNN probably has, let's say, 1 million followers on Twitter. So the degree of CNN, you can say, is 1 million. It's actually not 1 million here because only a subset of those followers will actually see that tweet. So let's say 100,000 followers saw that tweet. So CNN will basically spreading it to 100,000 nodes, and that's CNN's degree. How many nodes does it spread? Does it connect to? That's the degree basically. And then there's this notion of centrality. So basically, if there are, so let's say a node, the fake news goes from one starting point to an ending point. You want to see, is there any node that basically you want to see which nodes were actually very responsible for it. Like if those nodes didn't exist, maybe it wouldn't have spread. And you want to potentially Twitter wants to block these accounts, wants to redact their tweets. So Twitter will attack these nodes and basically like try to bring down the post or try to block the user. So this notion of centrality is also important, which basically says that in all the paths in the graph, which node comes in the most paths, basically. And then the next thing I'll talk about again is kind of related to social science. So it's basically about how we related to each other. So, and we can model ourselves as like, let's say we model each person as a node, and then we can, and here actually defining an edge kind of gets tricky, because how do you know, how do you say that two people are connected? Maybe they're connected if they've talked to each other. Maybe they're connected if they just sat beside each other on an airplane. Or are they connected only if they're friends? And that gets tricky to define in the real world. So there are multiple ways of doing this. And like, so this graph that you see here on the top right, that's basically something called, it's a concept called Erdos number. Erdos was a very famous mathematician. So people basically like plot, it's basically a famous concept where mathematicians who've published papers can be connected back to Erdos. And basically the idea is that for edges, they basically use people who've published together. So if two mathematicians have published together, then you can add an edge between them, and you can figure out like what is the shortest path from one mathematician to Erdos. And that was just an example. So obviously you can apply the same concept to social networks. So for example, you could, and this is actually easier. So for example, you could say that people who are connected as friends on Facebook are actually 1 degree of separation away. And the concept of 6 degrees of separation here is that in any graph, like any social graph like this, if you try to compute the average, like the average degree of separation between any pair of people, it'll actually turn out to be less than 6. And it's kind of surprising considering that the world has 7 billion people, and even like Facebook has billions of users, and you're probably friends with only 1,000 users, right? But even then, like the average degrees of separation is less than 6. And in Facebook, actually it's around 3.5 or 4 or something like that. And it keeps reducing because more people join Facebook, more friendships are made, and it actually starts reducing. So you can actually like check how efficient the social network is. Like if it has a low average degree of separation, then it's probably pretty effective. There are a lot of users on it. They're very connected to each other. And that's actually also, and again, so this is just to like highlight a layer of complexity. These edges can be complicated. Like for example, right now I'm talking to you. I probably don't know all the users who are looking at this talk. So you might not want to add an edge from me to you, but you guys probably know me. You've seen me now. So you want to add an edge from you to me, but not from me to you. So that's called a directed graph, because there's only one direction that you can traverse that edge on. So yeah, and it also applies. So like taking the example of Facebook and Instagram has followers, so you can follow someone and they might not follow you back. So that's basically a directed graph. Whereas on Facebook, both have to mutually accept the friendship. So that's an undirected graph because you can traverse on both sides of the edges. And so another interesting idea here is that you can think about how Facebook and Instagram recommend friends to people. And it's not actually very difficult to come up with a simple model for that. If you want to write your own social network platform, maybe what you can do is that maybe you want to recommend people who have, let's say, 2 degrees of separation, and you want to show up people who have less than equal to 2 degrees separation, and things like that, basically. So yeah, the concept of mutual friends that you've probably seen, that basically means that you have two degrees of separation between someone that you have a mutual friend with. So yeah, so that's about social relationships. And then some of you might be interested in economics and finance and stuff like that. So you can also apply this concept there. So here, basically what I've shown on the left is basically a graph of different stocks. And some of these are stocks, commodities, bonds. You don't need to know what they are, but basically stocks like Microsoft, Apple are there. And so why do you want to like connect them? Well, you probably want to connect. So what like people in finance actually want to do is they want to know how do stocks correlate. So let's say if Microsoft's stock price is going up, then it's also probable that Apple's stock price will eventually go up. Why? Because they're tech companies. Like if two stocks share an industry, they're probably going to rise together and fall together. On the other hand, it can happen that this correlation factor here, which basically ranges from -1 to 1, and the reason why it can be negative is that like sometimes it can happen. Let's say there are two companies which are like fighting in the same market, and you're pretty sure that only one of those two companies is going to survive. So you can say that when one company's stock goes up, the others will go down. And these are models that people actually study. And there's this whole, so obviously the graph can change with, like, it depends where you draw the edges. If you say that if the correlation factor is greater than 0.5, you want to draw the edges, this is one graph that can come. But if you make the correlation factor range from, let's say, 0.3 to 0.75, then this can start changing and you get different graphs for each correlation value. And people actually use this. So there's this thing called portfolio diversification in finance, which is basically an application of maximum independent set. And I'm not sure how many people actually use that, because it might get difficult to actually get these correlation values in the first place accurately. But there are problems in finance that people can study using graph theory. So now I'll talk about the internet. And this is something that we kind of don't appreciate enough. So what is the internet? The internet is probably the world's largest deployed graph, and people don't think of it that way. But like, the interesting thing is that right now, when I'm speaking, if someone, let's say from the United States, is tuning in, through these, which are underneath the sea. So these cables basically transfer from a data center in India to a data center in the United States at lightning fast speeds. Like, they actually go really fast, because that's how you can live stream. That's how I'm being able to take this talk. And so the thing to appreciate here is that every time you send a message to someone, to a friend, let's say abroad, the message is actually going through a cable which is underneath the sea, and it's traveling these huge distances under the sea. And I find that concept pretty amazing. Like, that's not something I had thought about, but this actually turns out to be true. And this is the graph of all these cables in the world. And on the right, I have this not very visible diagram, but basically it shows how these packets of data, the messages, let's say the video, all these are transmitted from one place to the other. So your laptop is probably connected to a Wi-Fi router, and that part of it is wireless, obviously, but after that it's all cables. So it probably takes it to a router, which basically like takes it to another router, which takes it to another router, and basically you hop from one router to the other till you reach the destination. So the whole internet basically works on this concept. And actually, routing as a problem, routing itself uses a lot of graph theory. Like, it tries to so the complication here is that each of these nodes don't actually know the whole graph. So like, imagine your small Wi-Fi router knowing about every device that exists in the world. It probably doesn't, right? So it basically uses a combination of concepts. So for example, in the Google Maps thing, I told you about how you can take larger nodes and then you can resolve them into smaller nodes, break them down. That's one concept that's used in routing. Another concept is that you basically only know about your neighbors. You don't know about the whole graph. And from there, you can basically start forwarding data. And it's actually quite ingenious how it does it. You can look into that. Each of these slides is obviously something that you can dive deeper into individually, and it'll take probably hours. You can like explore it for hours and you won't get bored. That I'm pretty sure of. So the next thing I'm going to talk about is something that I don't know much about. So, but I just know what these applications are. I can't explain to you. Don't ask me questions on this. But yeah, so it's actually used a lot in graph theory. Actually surfaces a lot in biology. So the cool part about this is that people didn't think about how biology works in terms of graphs until very recently. And that's true for a lot of fields, but it's also true for biology, because there are a lot of things that are coming up which are actually new research. So there's this whole thing so I'm pretty sure if you've taken any biology classes or like you've read anything about it, one key problem is that since there's so much to study about, there are so many different kinds of species, so many different kinds of microorganisms, it's extremely hard or nearly impossible to study about each of them individually. So you want to group them up into like classes. And like, if you've not taken something away from, like if you've not taken anything away from biology, this is probably something you should know, because that's the interesting part. You want to cluster things together that you can study together, and you want to find properties that apply to a lot of things at once. And this graph on the right actually shows that. So this is a graph of diseases apparently, and these diseases are like connected if there's a gene that's common to both these diseases. So for example, here there's something called muscular dystrophy and something else called something, I don't know how to pronounce that, but whatever. So basically these two probably have a common gene that causes them, and that's why they connect them together. And obviously, like, so, and again, like chemistry, there's this whole that you can use graphs in studying molecules, so that helps with molecular biology apparently. Then there's this whole concept of biological pathways, where like it turns out that people study it in terms of graph theory to figure out which pathways are important, which pathways can you block, so that, let's say, a disease like some harmful microorganism doesn't grow in your body. So people think about these pathways and they actually study these things. And then there's genomics, like I talked about genes, and yeah, so you want to see which genes are common between what species, what microorganisms, and the different, like you would have heard of the different strains of coronavirus, for example. So yeah, these are things that people think about. And then finally, there's epidemiology. So like at the early stages of the pandemic, you might have come across these tools that basically have patients as nodes in the graph, and two patients who basically, like if one patient contracted the disease from another patient, you basically can connect them together in a graph. So at least in the early stages of the pandemic, I saw a lot of these visualizations floating around. And obviously you can, like, it doesn't take a genius to figure out that now that is actually going to be a very difficult activity to look at those graphs, because there are millions of cases. But like back then it was important, like you wanted to track the spread of the disease at an individual level. So graphs were helpful there. And a related kind of application is brain and cognition. So I'll start by this term here. I'm pretty sure that if I'm pretty sure you hate me for putting this here, because it kind of provokes these very negative, it forces you to think about very negative things. It probably makes you sick. And this is actually a study in psychology that basically words like these basically trigger ideas in your brain which are connected. So for example, these two words could be connected in your brain to sickness. The idea of bananas might get connected to sickness. It happens for me, it might not happen for you, but it is like noted to happen to a lot of people. And here I have a graph that shows basically ideas being connected together. So the whole concept here is there's something called so people think that our brain has an associative machine. So for example, if I say the word hot, then you'll automatically start thinking about the word cold. And you might not realize that, but it actually happens. And I'll show you an example of that in a moment. But basically the idea is that if something has a cause effect relation with something else, those two ideas are connected with an edge that basically describes an effect. Something can be a property of another thing. For example, if I say bananas, then you might also get primed for yellow. Primed here means that you basically start thinking about this on your own, and you don't even realize that basically. And I think it's quite amazing that so basically this whole research related to the brain is actually quite new. It started becoming popular in the early 2000s, and it's such an active area of research because we don't understand the brain right now. And like it's pretty amazing that after all that we've learned, we're all like trying to learn we're looking into artificial intelligence and all, but we don't actually understand how we think. And like so yeah, like a whole race that's trying to make computers think doesn't know how they themselves think. So it's actually a very active area and an interesting area of research, and graph theory pops up almost everywhere here. So there's this concept of so before that actually, so when you look at this word SO-P, so research shows that some people will fill it with A and think of it as soap, and that's probably if they've just had a bath, if they've just washed clothes a little while earlier. And if you've actually eaten just a little while earlier, you'll think about soup instead of soap. So all this is research. I'm not just making claims here. And so in the brain, there's this whole concept of a connectome, which basically is the project of it's basically trying to map out our whole brain. So neurons here are nodes, and connections between neurons. If neurons can like in some way communicate with each other, then you put an edge between them. And the idea of mapping the whole brain, all the wiring inside the brain, is actually called a connectome. And finally, you have at the end this concept of a small world network, and it's very similar to the 6 degrees of separation thing that we just saw before. So in the brain, it turns out that just like you're connected only to 1,000 friends, but are just 3 or 4 degrees of separation away from a lot of people, similarly, in the brain, neurons are actually not very densely connected. They're connected in a sparse way. So sparse here means that the number of edges is actually quite small. So one neuron might be connected to only 1% of the remaining neurons. But despite of that, even though that's a constraint, you can reach from one neuron to the other neuron with some sort of a message within just 3 or 4 hops. That's kind of similar to how you can reach from yourself to probably Donald Trump in just a few degrees of connection. And I'll actually show you an example of that later. But yeah, so the idea is that even with a small number of edges, you can communicate very fast between these neurons. And we have like millions or billions of neurons inside our brain. And this turns out to be an interesting aspect to study. So I'll now come to the more CS side of the applications. You've probably seen, like some of you might have seen a neural network before, and this is basically at the heart of artificial intelligence. And so basically, like at the very fundamental level of artificial intelligence, you have these graphs, which basically, and these are actually called neurons. That's why it's called a neural network. And you can clearly see these are nodes, and they are connected to nodes in a different layer. And it turns out that like there have been studies that show that the first layer, basically, like if you're trying to recognize an image, the first layer might like just figure out what the lines are, what the edges, what the dots are, and things like that. And then later layers actually start combining that knowledge into objects and use this to identify objects. So it's all working on the basis of graphs, and between each node you will probably have some weights, which basically try to propagate information from one place to the other. They say how much is this neuron's value affected by the value of some other neuron. That's going to be the weight. That's what the weight on the edge signifies. So yeah, artificial intelligence also at its heart has graph theory. And lastly, the interesting thing is that all of knowledge basically can be thought of as graph theory. So I talked about how ideas can be connected together in the brain using graph theory, and you can study that. And very similarly, there's this project called the Semantic Web, which had a lot of traction 10 years back or 5 years back, but recently, like it sort of lost traction eventually. But even right now, it's being used actively by companies like Google and Facebook, and they're trying to figure out how to exploit this technology. So the technology basically is that we have all this. You've probably heard of big data, right? We have all this data that is being generated. We want to exploit this data, but since this data is very messy, like just this video call produces megabytes of data, and like if you look at all the data on the web, it's probably going to be like terabytes and terabytes of memory. So it's very difficult for even computers to like study this randomly. Like they can't just study it like this. So you want to connect concepts which are similar using these graphs, basically, like we saw earlier. So here there's this is basically one type of graph. So you can have these different things as the nodes, and then these relationships between these things as the edges. So a software has a manual, a document has a topic, and basically a document can actually have many topics, and then a software might be part of a library. So things like that. So you can connect all these notions, and if you just feed raw data to the computer, to any intelligent algorithm, it might find it very hard to identify these relationships. But once you give this semantic meaning to them, once you provide this whole knowledge that humans easily have but computers might not have, they're actually able to do better. That was the whole hypothesis behind the semantic web, that we should use our data, we should organize our data in an efficient way using graphs. And so here I've mentioned some of the major projects within the semantic web. So some basically create graphs for music, some create it for news, some create it for there's genetology and stuff like that. So for all these different topics, you want to create these graphs. And these graphs basically I've taken from this website called 6 Degrees of Wikipedia. So the whole idea of this website is that so if you take every Wikipedia page as a node, and if you connect two nodes if they have a link between them. So for example, if you go to this graph here, basically if you've probably opened Wikipedia and seen hyperlinks, right? So if a page links to another page, you can connect them on the graph. And so 6 Degrees of Wikipedia basically lets you put any two terms, and it finds you all the paths between these two terms, all the shortest paths between these two terms, to be more precise, within seconds. So basically, here I plotted the graph from Delhi Public School Arkipuram to Donald Trump, and so it basically said that the shortest path is of just length 2, and that kind of gives you an intuition of how 60 degrees of separation works. But and it also shows how it made these connections. So it went from NASA, it went from Prime Minister Narendra Modi, and it went from stuff like Florida and all. And these basically connected together to take DPS Arkapuram to Donald Trump within just 2 links. And on the right side, basically, I just try to show you that so this was this here the two terms are I asked for the shortest path between Kenya and graph theory. You probably can't see them because of how messy the slide is, but I apologize for that. But basically, the idea is that even if you would see this graph, you won't be able to make out much, right? There are approx 150 paths from Kenya to graph theory, and this is even though the length of these paths is just 3. So just going from length 2 to length 3, you have this explosion of number of paths, and that probably gives you an intuition of how we can reach different, like any person in the world within 6 degrees of separation or something like that. So yeah, that was basically the idea. So those are some of the applications that I wanted to take you through. And so the idea is that these are just a small subset of applications that I personally find cool, and hopefully you do too. But graph theory is applicable in so many places. Like it's applicable nearly, I'm pretty sure if you put a random field on the chat and towards the end of the talk, I'll be able to at least think of some application where think of some scenario where graph theory can be applied. So there are a lot of these applications. You can look into each of these and study about them, and hopefully so I have not gone over the details, but you'll find that the details are actually quite interesting. So now I'll just quickly go over some of the important subclasses of graphs, which basically this is important because general graphs, like you saw in the previous slide, general graphs can get very messy. But you want to look at some subclasses of graphs which actually are easier to compute on, which are easier to think about. So here I've shown you examples of grids. So the example in the slide here is of a grocery store. You could, this particular image comes from this Walmart hackathon, which they wanted people to perform some task on this graph. I'll probably describe that in a minute. But the idea is that you can model it as a grid. What is a grid? A grid is basically a graph where you can split it into these rows and these columns and rows, and you have these cells which are connected to each other if they share a side, if they're adjacent, they're adjacent if they share a side, you can say. And and it turns out to be a useful way to think about things. So for example, Walmart's hackathon, they wanted us to think about where they should place their products, and they have this whole store where they have these shelves and stuff, and they want to place the products in such a way on these shelves that people it basically should be profitable for them. So here the interesting the counterintuitive kind of thing is that Walmart actually tries to place its goods so for example, what do people buy frequently? They buy grocery frequently. They buy, let's say, they might buy things like chips frequently, but they might not buy teddy bears very frequently, right? So what Walmart actually wants to do is it wants you to spend the maximum amount of time on their store. They actually want it to be harder for you to get to the thing that you want to purchase. And that's not because Walmart is evil. It's because it maximizes their profits. So for example, if let's say you want to buy meat, and this is the entry and this is where the meat is. Now you have to walk from all the way from here to here, and you'll probably encounter 5 different products on the shelves which might not be on your shopping list, but on seeing them you might feel like buying them. So the whole idea is that if you spend more time on their store, if you spend more time roaming around, you'll see more things and you'll end up buying more things. So yeah, the whole idea was how to maximize the time that people spend on their store. And yeah, so I've just shown how you can actually start solving these. So once you have a map, you can convert into let's say black and white, and like this you can generate using some libraries using Python or something, and from there you can start analyzing this graph and computing on it. And I've talked about grids earlier also. Like I talked about mazes, I talked about object detection, and object detection actually generalizes. If you look at any image, an image is basically a grid of pixels, right? Like it's like you can, so once you start thinking about it as a grid of pixels, you can do like a lot of vision processing algorithms, at least the primitive ones before like deep learning took over and started being applied to almost everything. The all these vision algorithms basically used they use this concept of representing an image as a grid and computing on that. And you have some information about each node. So again, your pixels are your nodes, and you have information about its color maybe, and you can compute using that. You can find interesting things like we did in the object detection example. And yeah, that's basically it. So now one of the most important subclasses of graphs that like this is something that you really should know about is trees. And these are not the trees, these are not plants. These basically look like plants in some ways because this looks like branches on a tree. If you like invert it, if you flip it around, then it looks like a tree. And again, so the whole idea is that so there are basically some properties that trees provide you which make them like attractive to people who are analyzing graphs. So for example, you can say that a tree will always, so if there are n nodes in a tree, there will always be n minus 1 edges. So if you have a tree with 5 nodes, it will always have 4 edges. And that's because of the structure of the tree, because in a tree, each node has a parent. So for example, let's say this node, I'll tell you what that means later, but this node has exactly one parent. Any node here has exactly one parent. That's what a tree is basically. And then you can quickly figure out that since every node has exactly one parent, so if there were n nodes, that will give you n edges, but the root node of the tree, basically the top node here, doesn't have a parent. So that's why you subtract 1 and it has n minus 1 edges. And then these trees actually end up having a lot of cool properties that, for example, if you want to go from a particular node to another node, and let's say you want to take a simple path here means that you don't want to repeat any of these traversals. If you go from NP to S, you don't want to come back to NP. You want a simple path. Then actually between any two nodes, there will always be just one simple path. So from here to here, the simple path is probably something like this. So yeah, the idea is this is actually a very useful property, but I'll not bore you with the properties more. You can look into them later, but I'll straight away skip to the applications. So one application on the left here is that all of our grammar, all like any language basically works on this concept of syntax trees. So how you order words in a sentence can actually be modeled using these syntax trees. So I'll just explain this image here to you so that you get an idea. For example, let's say the root node here, the top node, is a sentence marked by S. And if you can quickly go over the sentence, it's basically my parakeet drinks mimosas in the morning. I don't know what that means, but yeah, that's an example sentence. So if you can actually break this sentence down into like components and analyze that with a tree. So here, my parakeet is actually a noun phrase, which can further be broken down into a possessive pronoun and a noun. Basically, possessive is my and the noun is parakeet. And similarly, you have this whole verb phrase, VP, which basically is drinks mimosas in the morning. This is all one phrase. And it can be broken down into the actual verb, drinks, and then within it also has a noun phrase. And here you have that thing mimosas, which is basically the noun phrase here. And then you have a preposition phrase in the morning. And yeah, so basically you probably get an idea. And why this is useful is that since you can like analyze all languages, all sentences like this, one helps in computation, and not just computation, it just helps in the study of how languages are formulated. So for example, English is pretty complicated, right? Like so the funny part is that I could extend this infinitely. Like inside this verb phrase, I can put any number of noun phrases, and inside each preposition phrase here, I can put any number of noun phrases. So you can think of it as extending infinitely, but all this we can model with a simple tree. And another interesting application is of BODMAS, and I'm pretty sure all of you've seen this before. So what happens when you input 8 divided by 2 into 2 plus 2 into a calculator, right? So this this is a typical problem of BODMAS. You have this order which basically says brackets, then division, then multiplication, then addition, subtraction, and all that actually is computed using trees. So for example, on the left, I've shown you one possible bracketing. This is how actual BODMAS works, and the right one is a different bracketing. So here you can see that you've written this whole bracket within this subtree. So a subtree is basically the tree. If you cut off the whole tree here, then this whole part is a subtree. So you've modeled it basically as 8 divided by 2 so all the numbers themselves and the operators are nodes, and you can basically go from 8 divided by 2. You can compute what comes here. You can compute whatever the result is here and put it like over here, and let's say you put 4 here, and then this side you can compute 2 plus 2 and put 4 here. Now you have 4 on both these nodes. You can multiply them. 4 into 4, 16. That's how a calculator actually does it, and how a computer does it. So on the right side, you have a different bracketing. So you have 2 plus 2 first, and then here you get 4. Then you have 2 into 4, 8, which comes here. Then you have 8 divided by 8, 1, and this comes here. So all these things are actually done by the computer. And in some sense, this concept has been evolved. This concept has evolved from just trees to actual graphs. So there's this whole concept of computation graphs, which is actually how neural networks work. And yeah, and again, like coming back to computation on this side also, programming languages also, like if you've ever coded in C or C++ and wondered how a compiler, if you don't know what that is, you can ignore this, but how a compiler actually like figures out how to perform all these instructions, it basically uses a graph underneath to figure these out. And I won't go into why that's a graph and not a tree, but the simple intuition is that you can call one function you can call from one function another function, and that function can call some other function, and then you can loop back. So if you see this tree, there are no loops here. You can't basically you can't basically connect a node to itself using some path, but that can happen in programming languages. So there they use a more general graph. The last subclass that I'll talk about here is bipartite graphs, and this is close to the end of my presentation. But the idea is that, let's say you have some, like if I have to give an example, let's say you have some boys here and you have some girls here, and let's say they're all heterosexual. So you want to basically make couples out of them. Now, so there are different ways to model this problem. So one way to model this problem is like, maybe you could say that you just know that boy 1 wants to be with girl D and E, boy 2 wants to be with girl A and B, or something like that. You just know that which girls a boy wants to be with and which boys a girl wants to be with, and you want to basically form couples so that the maximum number of people so people don't remain alone. They basically get matched up. And this is not typically how things happen in real life. You never probably get a bunch of N boys and N girls, and you never have to match them together, but you can figure out how this can be of importance. And again, this was a simple modeling. I just told you who likes who, but it can get trickier than that. So for example, in this picture itself, it's basically showing the preference order. So for example, the boy 1 really likes girl C, likes girl B a little lesser, likes girl E even lesser, and things like that. So this is an ordering of the boy 1's preference. And similarly here you have a ordering of the girl's preferences. And the idea is you want to make couples so that so that it's a stable marriage. It's called the stable marriage problem. You don't have to marry them, obviously. You can make couples for anything, but the idea is that you want to map one boy with one girl, and so that it shouldn't be that basically, for example, here, if you end up mapping boy 1 with girl A, and so and let's say girl E is mapped to let's say boy 4. So you can clearly see that boy 4 really doesn't want to be with girl E, and whereas boy 1 would actually prefer being with girl E, whereas boy 4 would actually prefer being with girl A. It has A before E, and here you have E before A. So you don't want to create you don't want to match people in such a way that they end up that you can always do better. Basically, if you do that mapping, then you can always swap these things around. You can once you swap them, then you'll always get a better matching and people will be happier. So the idea of a stable marriage problem is that you want to create a marriage so that both on the boy side and the girl side, there's not a way to flip things around that it becomes better. And this is actually a very hard problem. Like we don't know any efficient way to solve this. So, and like from like, since I'm talking about hard problems, I'll just like also talk a little bit about the field before I end, in case like some of you want to actually go into the theory behind all of these things and not just think about it as a concept and as the applications. So the field basically, from like what I've seen till now, has these 4 basic components if you want to actually study graph theory. So you can mathematically analyze properties, and then like, so for example, properties like the tree one, like I showed you that a tree always has n-1 edges. That might not look like complicated math to you, but that's something that comes from math. And graphs actually have very complicated properties that mathematicians actively study, and it's definitely not a closed field. Like all of graph theory is still evolving. We get new discoveries almost every year. So you can look at them. If you're interested in the math and the logic part of it, you can definitely check this out. There's the algorithmic part of it, which I'll also describe here in a moment. But it's basically like, how do you solve these on real data? How do you actually compute stuff, like the shortest path? And then it's used for probabilistic modeling. Like, so for example, one way to look at your neural networks is saying that it tries to maximize the probability of classifying things correctly. So if you start putting probabilities on the edges of graphs and like events at the nodes of graphs, I'm sorry if you've not seen probability before, but events and probability values are things that happen in probability and statistics. So you can basically use graphs to analyze these probabilistic models and come up with solutions to various kinds of problems. And lastly, there's this whole field of algebraic analysis. Like if you're a high schooler, you probably haven't heard of these things. So I won't go into them, but yeah, that's one field. And talking about algorithms, like we know that there are efficient algorithms for things like finding a shortest path. We have very efficient algorithms for that. And there are these 2-3 other problems that if you like plan to study about graph theory after my talk, you can like search these up and read about them. I won't describe them here. And then there are some hard problems that we don't know efficient algorithms for. And some of you might not know what efficient means, what algorithm means, but you can just think of it as slow algorithms and fast algorithms. So these things are harder to solve. So it turns out that actually drawing a graph is pretty hard. Like if I give you a description of the nodes and their edges, like I list them out to you, drawing that graph on paper can actually be very hard, and even a computer can't solve it very fast. And also interestingly, if I give you 2 graphs which are drawn and I ask you like, are they similar? Like, are they the same graph or are they different graphs? Even that can get really confusing. And like, if you try, I don't have examples here, but if you search up the net, you'll find examples for this. And it's something that even computers can't solve efficiently. Then you have these problems like independent set, graph coloring and all, and this problem called traveling salesman and vehicle routing and stuff like that. Again, you can search these up, look at them. And like I can probably give you an example of routing, for example. So if you've ever traveled to a different city, you might have heard of hop on and hop off tours. So the idea of the whole tour is that you want to take people from one monument or one like tourist attraction to the other, and you want to create this whole route that takes you across all these monuments in the city, and you don't want people to look at the same things again and again. So it actually gets kind of hard to like create a route that takes you from that covers all these monuments and does them quickly. Like you don't end up looping around, and you minimize the length of the tour basically. But also at the same time, you don't take people across the India Gate twice. Like that'll get boring, right? If you have to look at the India Gate twice as a tourist, that will probably get boring. So yeah, these are some of this. This is just another application that comes to mind when I talk about routing. And this is actually a hard problem. So like real hop on hop off tours can probably do it because they have a very small number of nodes and edges. Like they might have 20 monuments. But if you generalize it to larger graphs, it gets very, like the algorithms get exponentially slow. So that's basically it. That's all the content that I have. And what I want you to take away from this talk is that graphs are everywhere, and it's like probably like I think it's necessary that people should know how to think about them. And it's pretty sad that a lot of people might never study graph theory. So if you're not taking the math course or the CS course in university, you probably might never like think about these things in terms of graphs. But I think that's a very useful abstraction, and there's a lot to gain from doing it for people across fields, across streams, studying different subjects. And a lot of these fields which actually have a lot of applications turn out to be like, some people find them boring sometimes. So for example, this obviously changes for people, changes from people to people, but like for me, bio can be like, bio gets pretty boring, but like it has a lot of applications, and I don't deny that. So things that have a lot of applications, that like bio is probably one of the most useful fields that is out there, but like many people don't like that. But at least for graph theory, I've not come across people who've not found it interesting, who've not enjoyed it. And like even like in university, a lot of people take CS classes, take math classes, and like some people might like one class but not another topic or something like that. But graph theory, I think almost everyone enjoys to some extent, and that's kind of like, that kind of makes sense because it combines. You need a lot of creativity sometimes. You also need logical thinking, and it's there's a lot of visualization going on. So sometimes you like, I've noticed this, that I often just don't need pen and paper to solve a graph problem. Like if I'm sitting in a car, or like if I'm sitting like basically unable to do anything else productive, I can like take up a graph problem and like start thinking about it. Because as I told you before, drawing graphs can get hard. So even if you have pen and paper, sometimes it's pretty useless. And there are no basically algebraic manipulations that you see across math. Like a lot of math is just algebra, and luckily graph theory is not like that. So you might find that interesting, and you've already seen all these applications. So thank you for listening to this long monologue, but I'll take questions right now also. And if you have like further questions, you can mail me. My email ID is here. And like if someone from the Exun team can put it on the chat, it will be easier for people to copy paste. And also like, please, like since I'm just in college, I'm also learning myself. So if you have any feedback about the presentation, about the content, you can send it in anonymously if you want to. Like this is the handle that you can send anonymous feedback on. That will be really helpful for me. So if you have any questions, you can probably, yeah. Yeah, so what inspired you to start your journey in the field of graph theory? So basically, like I mentioned before, it probably started off very randomly because I was just preparing for this presentation that I had to give for an exhibition. That's where I first read about it. Then I started like doing competitive programming. That it like I learned about a lot of these graph algorithms. So I entered it from a very like CS oriented perspective. But then I like went on to do a lot of these projects in school, as well as like recently in the summer I was doing a project, and all these like somehow coincidentally all of these involve graphs. So maybe it's because I chose those projects because I like graph theory so much. But yeah, that's kind of how I started exploring graph theory. And about learning graph theory, well, so you can basically look up some online course if there's a dedicated course to graph theory. Otherwise, like if you in for more casual sort of learning, you can, there are some cool videos, my number file, and YouTube channels like that which talk about graph theory in a more casual way. And then if you want to study the math of graph theory, pick up a math textbook. It'll have a lot of fun problems. And yeah, maybe I can like if you can drop me a mail, I can give you more direct pointers. So any other questions? Okay, so can you suggest some small projects to try as a high schooler to explore applications of graph theory? Yeah, I mean, you can do a lot of things. So for example, I'll talk about something that I have done, maybe because it's like difficult to tell you how you can find things. But so I'll tell you how I did this. So basically, just if you are like interested in any problem, like or a particular field, for example, some people might be interested in so I was personally interested in language. So that's how I picked up my first graph theory project probably. So like I've shown you before, language can be modeled as graphs in a lot of ways. And that's how I basically like, so my first project was basically like you have speech recognition, right? And in speech recognition, it gets confusing if the speaker is saying two words that are very similar. So like words like, I don't know, sea as in the ocean sea, and let's say see as in seeing this video. These can get difficult to disambiguate. So obviously language models can like infer the whether it's a verb or noun and things like that. But in some words, that's also not possible. So the idea was that I made a graph, like if I make a graph between all these words that sound similar, that are difficult for the speech recognition model to pick out, then maybe you can come up. So maybe you can come up with a particular set of instructions. So for example, if you're making a robot that works on speech recognition, you can come up with a set of commands which don't have two words which sound very similar. And that becomes an application of graph theory, because now you have these words as nodes and you have these edges between them if they sound similar, and you want to pick nodes that don't sound similar. And that's actually the independent set problem, which I did mention as being quite hard. So yeah, that was one project. So again, just look for things that you want to look for, a problem that you want to solve, and you'll if you look at 5 problems, you'll probably find one where you can apply graph theory. For AI, how do algorithms added between the input and output layer work? So this is basically like a very intro to AI kind of question. So you can probably check out how neural networks work, but the basic idea is that each node has some information. So your first layer of nodes will have some information, and the next layer of nodes will have so each node contains some information that can be used to make predictions. So for example, if you're categorizing something as a dog or a cat, your final output layer nodes will basically output something that tell you whether it's a cat or a dog. And so to propagate this information from one node to the other, what you try to do is that, let's say layer 2 will basically take the values of the layer 1 nodes it's connected to, multiply it by the weight that is on their edge, and use that computation to figure out, compute its own information. And it turns out, using just this simple concept, you might not have understood it fully, because describing a neural network like this without visualizations gets hard. But just something simple like this, basically a computation graph, is what a neural network is and what AI works on. Again, there's this very cool video by 3 Blue 1 Brown on neural networks, which explains this much better than I can right now, and you should probably check that out. Any other questions? So this question is basically about we here got scared that graph theory might be very complex. So I'd like to say that since I tried to compress all of this all these applications, all this knowledge into a 1-hour talk, which ideally should be a whole university course that lasts 4 months, if you go into the details at least, that's probably why you felt that it was very complicated. But if you start from the basics, pick up, let's say you're doing it from a book, you could do it in whatever way that you find interesting and you are motivated to study in. But let's say you pick up a book and start reading, they'll build it up very systematically, they'll define things for you, and then slowly they'll start talking about different types of graphs, different properties. And it's actually not that hard. If it's I personally find it a lot easier than most of the math that's taught in, let's say, grade 11 or 12. So just try to do it, you'll probably find it not that difficult. Okay, I heard about algebraic analysis and I thought about graphing calculators. Do they function on the same basic principle? So I'm not exactly sure how graphing calculators work. And graphing calculators, I think you mean calculators that plot graphs, the statistics graphs, and not the networks graphs that I talked about right now. And so obviously graphing calculators, sometimes they can do a lot of these algebraic computations like matrix multiplication and stuff like that. I'm not sure how they actually work inside, but they can perform algebraic analysis to some extent. And I don't know how to answer this question better, but yeah. Okay, I'm glad to know that you found it interesting. And again, if you want more pointers to how to explore it deeper, you can always drop a mail to me. Is 23andMe an application of graph theory? Any idea how it works? Actually, I don't know what 23andMe is, so I don't think I'll be able to answer your question. But again, I'll check it out later. is graph theory related to symbolic computation? Um, so again, I'm not exactly sure what you mean by symbolic computation. So yeah, I probably can't answer that question right now. What was your age when you decided to go with graph theory? So yeah, the interesting thing about graph theory is that I don't think there's any age that you need to be to like learn about it. There's no prerequisites as such. It just needs some logic and some thinking that like I think anyone can do. So I personally started again like in grade 9 or 10, but yeah, probably grade 9. But like you could do it in grade 6 also. I don't think that is a constraint. You basically don't need any other topics from math that are taught in school. What's a more efficient strategy for a social network? One-sided following or two-sided friendship? I think this interestingly, Facebook also has one-sided following, right? You can like pages, you can follow people who might not follow you back. Though mostly people on Facebook tend to look at it as the main concept of Facebook is adding friends. So, but if you want me to think about would Insta work better, I'm sorry, there was a call. But yeah, if you want me to think about how Instagram, whether Instagram should have done this like one-sided following or undirected graph, well, I'm not exactly sure, but I think one-sided following has to be there as a feature because a lot of Insta's business model is people following celebrities or like people following people who are into modeling or something like that. So one-sided following probably works better there. But in some cases, like LinkedIn, also like if you look at even LinkedIn, it also has one-sided following to some extent. So I think one-sided following always needs to be there. And the plus side is that if you have one-sided following, then you can always create two-sided friendships, things like that. Because like if you so let's say you want to connect A and B, you can go from A to B. Like A can follow B and B can follow A. That's how Insta works. So I think one-sided following is more general, and that's probably why Insta chose to work with it. Have you personally used graphs to solve? Yeah, I've used like yeah. So obviously, like I've used graphs for a ton of problems. Like I said, I did a couple of projects in school which use graph theory. I've done a lot of things in college, which like even though I've just been in college for 2 years, I've done a lot of like assignments and projects in college which were actually related to real life optimization problems. So for example, like in high school, I probably like tried to model like for a competition. I just made this like model for garbage collection, and that used graph theory because like you want to route your garbage collecting trucks from one place to the other, and that's where graph theory comes in. And again, like things like ambulance allocation, like a lot of these basically routing problems are all part of graph theory. So for example, that's how the whole of Uber works, how all these you'll find graph theory in a lot of real life applications, and like I just showed them to you, and you can pick any of them as a project. So yeah, I've done it in some things, you could do in some different things. Yeah. Won't a program based on graph theory become too resource extensive after a few hundred nodes? Okay, so not after a few hundred nodes, because like if you're not aware, our computers these days like can perform about 1 billion instructions in a second, and yeah, that's basically a normal computer. Now obviously that doesn't mean you can feed in a graph of 1 billion nodes and try to run something, because 1 billion nodes also probably means gigabytes of data. So there's two sides to it. One side is that there are two resources basically. One is time, how long does it take to compute, and that depends on what you are trying to compute. So if you like, some algorithms run faster, some algorithms run slower, so that depends on that. And some problems we don't even have algorithms for which can run faster, which can run fast enough for let's say 100 nodes. But on the other hand, you have this issue about data. How do you store these large graphs? For example, I showed you the Google Maps example, and it's Google obviously has a lot of data centers, and it takes a lot of data resources to store the whole graph, like to store the whole map of the world. And especially like if you're going down to the address level, So if you just have cities, then it's easy. Like probably there are thousands of cities, you can still store them. But once you go down to the address level, you have billions of just nodes. So that gets complicated. Yeah. Yeah, actually, computers solve not arithmetic equations per se. Arithmetic equations, you probably mean something like left hand side and right hand side and stuff like that. So I'm not sure about equations because that probably some part of it gets solved using linear algebra, and that's not exactly graphs. But um, yeah, computers, these computations, basically the addition, subtraction, division, and all, they can, all the bracketings that you have to do and take care of, that can happen to through trees. And I think, yeah, even today calculators use trees basically. Are there applications of graphs that we've been using all along without even realizing? Yeah, graphs are in your like. Okay, I'll answer apart from the slides, but like in the slides itself, I've mentioned some of these. For example, your brain uses graphs inside, and you don't know about it. You're probably thinking right now using some sort of graphs which people are actually analyzing. Like it's not like the graphs just exist, people are actually using that. And so applications of, again, so about applications of graphs that you've not been realizing. So if you've checked Twitter, for example, like how do posts get recommended to you? Well, like how do they turn up in your feed? That's probably happening through a graph algorithm somewhere, because they look at which friends of yours liked the tweet and things like that. So all these recommendation systems kind of use graphs at some level. Also Google search, like Google search, at a very basic level, links, you could think of the pages or the individual websites that it takes to as nodes. And the initial algorithm at least used this concept of how many links that go from one page to the other. They use that to basically come up with a model that could come up that could present good search results. I don't know how they work now. And there's a lot of linear, so like I mentioned, there's a lot of algebraic analysis plus graph theory combined that goes into a lot of applications, and Google search is one example of that. So yeah, that's one application. And I can also come up with things outside the computation scenario, like outside CS. So for example, let's say so how does water come to your home? Like it comes through some pipes, but this whole network of pipes is actually an engineering problem. Like how do you lay out this network of pipes? So all these are applications of graphs. And how metro works, like if you live in a city that has metro routes, how train networks work, all these things basically have some level of graph theory underneath them. Obviously a lot of people might not be thinking about them in a graph way. I don't know if they are actually doing that for Indian Railways, for example. But if you do that, there's a lot of scope for optimization that people might not be like making use of right now. Are there any real world applications of obscure graph algorithms such as HLD and bridge trees, among others? Um, okay, so like if you don't know what HLD and bridge trees are, you can either ignore this question or you can check that out later. I would like not recommend checking it out till you have at least some background in graph theories, because these are advanced algorithms. But real world applications, I'm not sure about HLD. I've not come across anything, but bridge trees, I think yes, you can like that. That's something you can use for a lot of things. For example, I did talk about this thing, right? That there are some like in a lot of applications. For example, the spread of misinformation. You have these graphs where you want to like block a particular communication channel. Or for example, in biology, I said that you want to sometimes block a particular pathway between two things. And bridge trees basically give you a framework for doing that. Like you have these components and you have these like you have all these components connected by bridges, which basically are kind of a bottleneck, right? So wherever you have to identify bottlenecks in graphs, you can probably use bridge trees to some extent. Are the weights on edges in a network static, or they can change over time? So for example, in maps, like I said in Google Maps, you have edges. Let's say you start to model edges as you start to model the weights on edges as the time it takes to go from one place to the other. And that obviously depends on the traffic, right? Like how much traffic is flowing through those roads. So obviously the weights on your edges can change in that situation. And similarly, in a lot of other applications, you'll find that the weights are not static. Now, one way to look at this is that you can look at specific time instances and try to compute on those time instances, like recompute from scratch and solve stuff like from scratch. You take a completely new graph with static edge weights and compute on that. And that's obviously less effective in terms of an algorithm, but sometimes you can do that. On other occasions, you might want to like check what's the effect if I just increase the weight on one particular node. And you can probably like understand that Google Maps probably doesn't compute everything from scratch every time traffic changes a little bit. So yeah, there are algorithms that also tackle that kind of situation where you want to compute something, but the weights, like one edge might see a change in weight, but the others remain same. Oh, okay. So what's the oldest application of graph theory? The oldest I can think of is PageRank. Again, graph theory is not limited to CS. So I think the older applications of graph theory was about urban planning. How do you like lay out your city? How do you lay out the sewage network in your city? How do you again, all these logistics things, how do you send water and where do you place markets? All this urban planning thing is probably, I think, some of the oldest applications of graph theory would be here. Also, it depends on what you mean by old. If you mean when people use them, then yes, this. Otherwise, like there are also applications which try to model how species evolved. Now they're going back to like thousands of years, right? They're trying to map out those processes. They've been done today, but they're actually trying to map out history. Also, again, so graph theory, I think as a field, it started like it probably did start from Euler, but Euler is one of the first people that did a lot of study in graph theory, and he was actually trying to solve this very like one of the problems that is pretty famous is the 7 bridges of Königsberg. And you can like Google that. So yeah, I can't type that out right now probably, but yeah, the 7 bridges of Königsberg, if you like search that, you'll find that that was one of the first problems in graph theory that people studied, and this was hundreds of years back. So any other questions? Okay, so thank you guys. Thank you for listening. I hope you're motivated to like check this out further. I hope I've at least motivated 10 or 20% of you to study this further. And you can always reach out to me, and don't forget to like send in any feedback.
Thank you for a really interesting talk, Shashwat, and also thank you to everyone who attended and took part in the Q&A session. That's it for today. Thank you.